Good morning, everyone. I welcome you all for Faculty Enhancement Webinar Series 2, organized by EEE Department, MSEC. I am Vanati, Assistant Professor of EEE Department, hosting this webinar today. We have two sessions today. For forenoon session, we have the webinar titled Electrical Vehicle Technology, and we have Industry 4.0 for afternoon session. We have few minutes left for the session to start. I request our department head, Mrs. Soundra Bala, to deliver welcome address for this session. Over to you, ma'am. Good morning, everyone. I welcome you all for Faculty Enhancement Webinar Series 2, organized by EEE Department, Meenakshi Sundarajan Engineering College. I'm Vanati, Assistant Professor of EEE Department, hosting this webinar today. We have two sessions today. For forenoon session, we have webinar titled Electrical Vehicle Technology, and we have Industry 4.0 for afternoon session. We have few minutes left for the session to start. I request our department head, Mrs. Saundrabala, to deliver welcome address. Over to you, ma'am.
We're unable to hear anything.
I can hear you, sir. There is
Bhaskar sir.
Yes, ma'am.
சொல்லுங்க மேம். பண்ணிடுறேன். Bhaskar sir.
Yes, ma'am.
Yeah.
I can hear you, ma'am.
Yeah. Okay. Good morning to our dearest secretary ma'am, beloved principal sir, and respected dean academics, esteemed professors, staff, students, and fellow teachers. Good morning to one and all. On behalf of EEE Department of Meenakshi Sundarajan Engineering College, I welcome you all for the event. I would like to extend my warm welcome and greetings to our speakers, Mr. Ganesh Shankaran, Chief Program Engineer, Ford Motor Company Limited, and Mr. S. Ramakrishnan, Senior Engineer, Ford Motor Company. Welcome you, sir. Thank you for taking your time out of your busy schedule and joining us in this webinar with the young minds who are very sure to learn a lot about the electrical vehicle technologies and take away better understanding that will guide them in discovering opportunities for growth in this post-pandemic world. The automobile industry is witnessing a dramatic change with advent of electrical vehicles. Today, the industry demands new skills and automobile engineering that could resonate with the paradigm shifts in the technical role due to the electrification of the powertrain. I am very sure this webinar on electrical vehicle technology and industry modernization is a walkthrough to these changing demands and is an opportunity for engineers to look for a better and brighter career. I once again thank Mr. Ganesh Shankaran and Mr. Ramakrishnan S, who have agreed to be part of this webinar and share their knowledge through this platform. I welcome you all to today's presentation. Thank you. Over to you, Vanati madam.
Thank you, ma'am. Now, we would like to introduce our speakers. I would like to call Mr. Bhaskar to introduce our speakers of forenoon session. Over to you, sir.
Thank you, Vanati ma'am. It's my great pleasure in introducing the chief guests of the forenoon session. We have with us Mr. Ganesh Shankaran, Chief Program Engineer Programs, Ford Motor Company Limited, Chennai. Mr. Ganesh is a graduate in mechanical engineering, starting with his bachelor's degree from the University of Madras, followed by the master's in mechanical engineering in the specialization CAD in Periyar University. He has a PGDBA in Marketing Management from Symbiosis Institute, Pune, and at present pursuing his PhD in VMRF on battery electric vehicles. Mr. Ganesh has started his career as a lecturer in Mechanical Engineering Department at Sona College of Technology. He shifted gears from the academic profession towards the engineering profession as an advanced engineer R&D in Brakes India TVS. He was in the field of design and development of 2-watt by 3-watt disc and drum brakes. Following with the Ford India Company Limited as a powertrain engineer, then as interior and electrical engineer, PD launch lead interior systems. He has launched Ford Figo for export markets, PD launch manager, and he has launched Ford Global Fiesta and EcoSport Endeavour. As a general manager in PD launch, he has launched Ford EcoSport for USA and Europe. And as chief program engineer programs, he has launched EcoSport Sports, Aspire CNG, EcoSport, and Figo BS 6.1 vehicles. Put together, Mr. Ganesh has 20 plus years of automotive experience. Also, we have with us Mr. Ramakrishnan Sivasubramanian sharing the phone session with us, a senior engineer programs, Ford Motor Company Limited, Chennai. Mr. Ramakrishnan has bachelor degrees in electrical and electronics engineering from Coimbatore Institute of Technology, Coimbatore, and has a master's of business administration, operations and SCM from Loyola Institute of Business Administration, Chennai. Mr. Ramakrishnan has started his career as a manufacturing engineer, blanking and stamping department in Ford India. The electrical equipment like press machines, variable frequency drives, PLCs, installation and maintenance. He's also been the PD launch engineer, minor programs, has launched dual airbags in Ford vehicles, freestyle vehicle launch. He's been the PD launch engineer for major programs like launches of Ford EcoSport, refreshing action for India and USA. He is also the PD launch senior engineer, battery electric vehicles and connectivity, and currently working in battery electric vehicle technology and telematics cloud connectivity. Mr. Ramakrishnan has 8 plus years of automotive experience. We welcome you, Mr. Ganesh and Mr. Ramakrishnan. Over to you, Anati ma'am.
Thank you, sir. We are very happy to have them here for the session. Now it's time to hand over the session to the speakers. I request Mr. Ganesh Shankaran, Chief Program Engineer, Ford Motor Company Limited, Chennai, and Mr. Ramakrishnan Sivasubramanian, Senior Engineer, Product Development of Ford Motor Company Limited, Chennai, to give their presentation. Over to you, sir.
Thank you. Slide more, please. Good morning, one and all. Thank you for the introduction. So without wasting time, we'll directly get into the topic. So today, myself and my colleague Ram, we will try to cover you the basics of battery electric vehicles and what is the technology which is upcoming, and we will give you an overall overview about it. So with that, next slide. So I would like to just make a small disclaimer here. Whatever the contents that we show in the entire session, the pictures, the references, it's all taken from the public domains and some of the research papers. And the views expressed by myself and Ram, it's purely the individual views. So we are not representing the company's view or the industry's view. So please make sure, this information is confidential, and request not to use any references from the slides. Thank you. So with this topic currently, what the broad level of agenda that we will try to take through is I will start covering the global trends in the electric vehicles and the EV scenario happening in India, and a little coverage on India government's electric vehicle policy, mainly the FAME 2, and why electric vehicles are important for India. So with that, I will hand over the sessions to Ram, and Ram will take you through the types of electric vehicles, the advantages of battery electric vehicles over the internal combustion vehicles, battery electric vehicles system and selection, especially the motor and the battery side of it. That will be a more technical session, and future technologies in batteries. And Ram will stop there, and then I will take over the session again to take you through the final session, which is the challenges and opportunities in the battery electric vehicle. We will touch base on battery swapping and leasing programs. And from there on, we will open up the floor for more questions and answers. That's the broad level of agenda. So with that, I'll directly get into the global trends in EV. So the chart that you're showing it on the screen, it's an overview of how the global long-term passenger electric vehicle sales are going to be between the years 2015 to 2040. So the data is pretty much latest. I would say if you take the example of 2020, that's where we stand. If you see the total market globally, it's dominated by the ICE-based engines, which is internal combustion engines, likely diesel and petrol. So that's what the gray cell is all about. But what you see is from 2020, there is a gradual progress, and the curve is more linear. And if you go all the way to 2040, almost 50% of the total vehicle population, it's going to be dominated by either the plug-in hybrid electric vehicle or the pure battery electric vehicle. So the 50% will be dominated by these electrically propelled vehicles, and the reduction in the internal combustion engine is about from 100% to about 50%. So the expectation is, the segment is growing. That's very important. So by 2040, the projection is all about 50%, or more than 57% of all the passenger vehicle sales are going to be electric vehicles, of which the fleet segment is about 30% will be more of electric. So this data is projected by the Bloomberg. So you can just go through it when you find some more time in the net. Next slide, please. So this slide is another interesting slide. If you see how the changeover is happening between 2050 to 2040, if you see the trend is going in the downward for ICE engines, if you take it as 100 as a reference percentage, and for electric vehicles 0 as a reference point. So by 2035 to 2040, you see the complete changeover happens, meaning the EV will take over the total sales volume, compared to the ICE vehicle. So that's what you could see it on the slide on the left-hand side. On the right-hand side, what you see is how the electric vehicle among the different vehicle segments, like the buses, the commercial vehicles, the passenger cars, are going to grow. So you see the topmost curve is the buses, which is the commercial segment, followed by the light commercial vehicle. This segment is exponentially growing. You could see this is primarily because of the freight demand growth, because of the urbanization which is happening, the city restrictions, and the economy is growing, and rise of e-commerce. These are all the reasons why you see the potential of electric vehicles in the commercial segment is growing up. And one more point on the left-hand side chart, why you see a dip in the IC-based vehicles, it is primarily because of the newer and lot more stringent emission regulations are coming, which is putting a lot more challenge on the electric vehicles. So that's a reason why you see a decline in the ICE, and there's a pickup on the electric vehicles. Next slide, please. And this chart is pretty much the same, but the only thing is it is shown as a classification of how each country is performing, in terms of the EV adaptation. So as you all know, between 2015 to 2023, even now, today it is dominated primarily by China. China is leading the all electric vehicle markets, followed by Europe, and then US. And India, you see, it is very, very at the nuanced stage, so it is yet to pick up. The same thing, comparing a projection on a long-term basis, for example, the trend is changing. If I exponentially take the projections for 2040, the European market is likely to overtake, the China markets, and it is followed by the US market. So there are many reasons behind why. In China, there is an aggressive policy support by the government to push both at the national and regional level to encourage the electric vehicles in all the segments. And why there is an increase in the Europe? Because Europe is very, very particular about the emission and the carbon dioxide reduction initiatives. So they are aggressively pushing, again, a conversion or an alternative for the ICE-based engines to clean and green electric vehicles. So these are the primary reasons why China and Europe are already ahead of the race. Next slide, please. So let's quickly cover what is the EV trend in India. So comparing to other markets, we can't equate what is happening in global cannot just happen in India because of various factors in India. Because India, from an automobile industry today, we are standing at a 5th largest in the world, and soon India will likely to become 3rd largest, by 2030. And the India government has taken a lot of measures in working towards a shared, connected, and electrical mobility. And India as a market, it is very unique, and more of high-level vehicle sharing, public transport, those are all the areas where India market is more focused about. So with that, what you see on the left-hand side today, the classification of vehicles by 2019 or 2020, if you see, the two-wheeler is almost like 80% of the total vehicle population in India, and followed by the other passenger segments. So this puts us a little more challenge in India. So this is the reason why you see some of the taxi aggregators like Ola and Uber, they increase the number of rides. If you see the statistics, they were about 130 million rides in 2015, and it has increased to about 500 million rides in 2016. If you see, it is within 1 year, it's almost 3 times or 4 times it's increased. So which is totally accounting for 72% of the overall market. So these are all some of the important information. So when you think about how the EV market is likely to grow in India. Next slide. So another interesting fact is today, if you leave the actions, for example, if you leave the today, no electric vehicles, electrification is happening. So we will continue the business as usual. So if you see the BAU, it is nothing but the business as usual. And the transformative is what if I transform from the conventional ICE vehicles to electric vehicles? The total energy requirement is likely to come down by 64% when you migrate from ICE to electric vehicles. That is what you see, about a minus 64% drop. So not only the energy consumption is dropping, but also it is interesting to see there is another factor, which is the carbon dioxide, because for every vehicle which is powered by an IC, there is a carbon dioxide emission. But when you go to the electric vehicles, it is called zero emission or a zero tailpipe emission. So the same thing, if you do the business normally, so it will be about a 600 metric tons of carbon dioxide you will be emitting every year. But if you would have moved to the electric vehicles by 2030 with the same amount of population, you will be able to reduce about a 37% of carbon dioxide. So which is a good news, which gives a cleaner air, cleaner environment. So the Indian government has already released the policy for electric vehicles in 2018, and they have some of the major or the key objectives on the EV policies are primarily to reduce the overall oil consumption, which is primarily required for the crude oil for transportation. And it also helps and encourage people to adopt the electric vehicles and the clean energy vehicles. And the third one is, it is also important for the India to adopt the lot more newer technology and the cutting edge technology and do lot more thing on the research and development. And not only that, so this helps in the improved transportation for the common man. So for a person, he would like to move from point A to point B. So he doesn't care which vehicle that he uses it. For him, the matter is he need to move from point A to point B. So it is up to the automobile manufacturer to give them the right means of transportation, which helps both commercially and also from an environmental aspect. and it is also indirectly reduces the pollutions in the city. And as you know, India has got a lot more polluted cities, right, according to the survey. And it creates the EV manufacturing capacity among the Indian manufacturers. And the last but not the least, it helps in facilitating the employment growth because of the new or a sunrise sector, which is the EV. Next slide. So very quickly, if you see the latest numbers of electric vehicles sales in India, so I would request you to focus on the left top bottom. So the two-wheelers, three-wheelers, and four-wheelers, so of which it is almost 90% the electric vehicles sold in India are primarily three-wheelers, followed by the two-wheeler segment, and four-wheelers are at a very, very minimal stage. So, but this is just a recent trend. We need to wait and watch the sales growth and the sales potential, how the technology is going to grow after the post-COVID situation. So this is just an information for you, but let's wait and watch. But the point to be taken is, though we have a vision for making 100% electric vehicles by 2030, but the realistic estimation, because of all the uncertainties that we are going through, so any success between 40 to 45% of electric vehicle conversion by 2030 itself is a good attempt, and it is a lot more realistic. Next slide. So quickly, I'll cover you the Indian government policy, which is called FAME 2, which is the Faster Adaptation and Manufacturing of Electric Vehicles. What the government is doing is, the government is basically giving you incentives for producing the electric vehicles, for using the electric vehicles, and how you put up the infrastructure for electric vehicles charging. So accordingly, the government has released some of the money. That is what you're seeing it on the top thing. So what you need to know is, for example, let's take the right side topmost, which is the row number 3 for an electric four-wheeler. The maximum number of vehicles which will get benefited in the scheme is about 35,000 vehicles. For example, if you have an electric car which has got a battery of 15 kilowatt hour, so the maximum benefit is nothing but 10,000 rupees per kilowatt. So if you multiply 15 kilowatt by about 10,000 rupees, so the maximum benefit that you will get is about 1,50,000 rupees. Sorry, 1,50,000 rupees that you will get. And there is a clause, your maximum MRP should be limited to 15 lakhs. So the total amount of money that's been allocated for electric four-wheeler is about 525 crores. But this is not just for the manufacturers, but also there will be some incentives for the purchaser, which is on the left bottom. For example, if you are buying a two-wheeler, three-wheeler, and a passenger car, I have just given you an approximate incentives. For two-wheeler is about 20,000, for three-wheeler is about 50,000 rupees. So this is apart from the government's benefits or the factors of giving you GST discounts, and the state and the central government's policies on waiver of registration tax, road taxes. There are a lot more benefits that the government is giving to encourage the purchase of an electric vehicles. Next slide, please. So I will stop with this last slide, and then I will hand over the session to Ram. So why EV? So today the EV is the major driving force, or what are the driving force that is pushing electric vehicles in this scenario? Let the slide get loaded. Ram, could you just enter, please? Yeah. So the National Electric Mobility Mission Plan is already unveiled by the Union government, or the central government, by 2013. So, and not only that, there are a lot of projections and predictions happening by a lot of companies. And one such thing which I just would like to quote here, this is by Tony Seba. So he's an author of The Clean Disruption of Energy and Transportation. So his forecast by 2030 is all the new energy which will be provided by the solar and the wind, and all the new cars will be electric vehicles, and all these cars will be autonomous. It's a self-driving vehicle, and the new car market will likely to shrink up to 80%. This is a big number, and the individual car ownership will become obsolete, meaning the crux of this one is there is a trend towards moving to the renewable energy sources instead of the conventional energy sources. And there is a high thrust on electric vehicles. And the third point, you may agree or you may not disagree, especially for India, is the level of autonomous vehicles or automated vehicles are likely to come in India. But the point 4 is already happening. Today, if we see the Ola and the Uber, the individual car ownership is kind of shrinking, and people prefer to use the ride ownership or shared mobility. I think that is what his predictions are. So maybe I'll just stop here. and I will give the session to Ram to cover the rest of the slide, and we will connect back again. Ram, take it over from here, please.
Yeah, good morning, team. Thank you, Ganesh. Hope you're able to hear me.
Yes, sir.
Yes, sir.
Okay. So now we will go through the different types of electric vehicles, and all of these types of electric vehicles are going to be in comparison with that of the internal combustion engine. As we know, the IC engine is a conventional engine in petrol and diesel cars, in which the combustion of the fuel occurs with an oxidizer in the combustion chamber. So that is an integral part of the working fluid flow circuit. In IC engine, the high temperature and high pressure gases produced by the combustion force the piston in order to have a linear motion, and slider crank mechanism transfers this linear motion to the rotary motion, and the transmission is further used to transfer this rotation to the drive wheels. So this is the basic overview on the internal combustion engine. So the first level of electric vehicle is the micro hybrid. This is the lowest level of the vehicle hybridization. It uses the start-stop system, where the regenerative braking technology helps to stop the combustion engine when the vehicle comes to a halt, probably in a traffic signal. Here, the energy is stored in an auxiliary battery and is used to quickly start the engine when accelerated. So the next type is the mild hybrid. So these are the cars with internal combustion engine equipped with an electric motor generator setup in the parallel hybrid configuration, allowing the engine to get switched off when the car is coasting or also in the process of the braking, and yet it can restart quickly. The mild hybrids may employ regenerative braking as that of the micro hybrid, and it also have some level of the power assist features to the internal combustion engine, but they don't have the electric only mode of propulsion. And the next type is the hybrid electric vehicle. So these are the cars that combines a conventional IC system with an electric propulsion system. The presence of an electric powertrain is intended to achieve either a better fuel economy or a better performance when compared to that of the conventional engine. It also uses the regenerative braking technology, and with this, the kinetic energy is converted to electrical energy, which is stored in a battery. And they also use the start-stop system. And the hybrid vehicles produce less tailpipe emission when compared to that of a similar sized petrol or diesel cars. So the next type is the plug-in hybrid vehicle. So the only difference between the hybrid and the plug-in hybrid vehicle is it has the external connection by which you can have the connection to the power source, and the battery can be charged with the help of that. And the plug-in hybrid vehicle has a much larger all-electric range as compared to that of the gasoline engine or even other types of hybrid vehicles what we saw before. And it primarily helps to eliminate the range anxiety associated with all electric vehicles, because here the combustion engine works as a backup when the batteries are depleted. So the next type is the range extended electric vehicle. So these are the battery vehicles that includes an auxiliary range extender. Here the IC engine is used as a range extender. It helps to drive the electric generator, which in turn charges the battery, and this battery helps to drive the electric motor. So this type of arrangement, we call it as series hybrid drivetrain combination. So the next, last but not the least, is the battery electric vehicle. So in this, we'll be going through the in detail portion of the battery electric vehicle. These are the vehicles which uses the chemical energy stored in the rechargeable battery packs with no secondary source of propulsion. And the battery electric vehicles uses electric motor and the motor controllers for the propulsion. So they derive all the power from the battery packs, and thus they don't have any internal combustion engine or the fuel tank in this case. So we also have some interesting facts. Now we can see what is the range on the pure electric motor when we start from an internal combustion engine to the battery electric vehicle. So if we consider micro hybrid and even until the mild hybrid, actually the contribution of a pure electric motor in order to achieve a range is 0 kilometers. And the battery which are used in these types of electric vehicles are approximately 1 kilowatt hour, which ranges from 10 to 50 kgs. They usually use 48 volt systems. The hybrid electric vehicle uses an electric motor which helps to achieve an additional range of 8 kilometers, having a battery of 0.5 to 2 kilowatt hour with a battery weight of 20 to 60 kgs, and they operate in 100 to 300 volt systems. The plug-in hybrid helps to achieve 50 to 80 kilometers on the pure electric motor drive, having 4 to 20 kilowatt hour as a battery capacity, ranging 100 to 200 kgs, which contributes to 4 to 12% of the total weight, operates as 200 to 400 volt systems. So the battery electric vehicle, it ranges from 150 to 500 kilometers depending on the battery capacity. So they have the capacity ranging from 20 to 100 kilowatt hour, weighing 200 to 700 kgs, primarily contributing to almost 70 to 32% of the total weight. And they also operate at 400 volt systems approximately. So now we can see some of the advantages of the battery electric vehicle over the internal combustion engine. So electric motor, as you are aware, like they are 5 times more energy efficient as compared to that of IC engine. So it almost helps to achieve 90 to 95% of efficiency from an electric motor when compared to 17% from that of an internal combustion engine. Also, electric vehicles are far more reliable. They have fewer moving parts and hence cheaper to maintain. EVs have a greater packaging flexibility since the drivetrain systems are simplified when compared to that of the internal combustion engine. So the next advantage is on the cost of the battery. As you could see, the battery cost falls rapidly over the years, and this will eventually make the EV capital cost, including the battery, to be lower than that of the internal combustion engine in the near future. And it also helps the usage of the power during off-peak times, considering most of the EVs are charged during the night times, and helps to support the renewable energy, as what Ganesh explained. So the next important advantage is on the pollution, which every OEMs and the government are looking for from the electric vehicle point of view. The pollution is greatly reduced with EV introduction, which addresses the air quality concerns, and EVs with renewable energy, zero pollution from that, and it does not have any emission, zero carbon monoxides, hydrocarbons, which we call it as an unburned fuel mixtures, oxides of nitrogen. The particulate matters are not present. The particulate matters are nothing but the solid particles or the liquid droplets found in the air. The carbon dioxide emission levels is much less when compared to that of the petrol and diesel cars. So the next advantages are EVs are 4 times cheaper in terms of running cost when compared to that of an IC engine. Effectively addresses the import of oil, which is a dependent factor on the internal combustion engine. So it greatly addresses the energy security. It also helps to achieve a lower service cost because of the less consumables. We don't have any oil changes, spark plugs, the timing belts. Unlike the gasoline engines, electric motor does not require a routine maintenance also. EVs offer improved ride handling, responsiveness, and a ride comfort. This is primarily due to the low center of gravity. That's because of the battery packaging on the floors. And it has a reduced noise, vibration, and harshness issues when compared to that of an IC engine. And EVs also helps to generate instant torque right from 0 RPM to the corner point, what you can see. So this helps the EV to have a faster acceleration when compared to that of an internal combustion engine. So the next advantage is on the transmission. EVs have a single-speed transmission gearbox. So given the speed and the torque available over the entire range, multiple gear ratios are not necessary, which in turn reduce the transmission system complexity. So we don't have the torque converters, no clutch disconnects for electric vehicles. This in turn reduces the weight. Associated losses are also greatly reduced in this case. So for a same motor, the BEV gearbox can be optimized with the help of the final drive ratio in order to achieve a better launch performance, maximum speed, efficiency, and the drivability. So in this graph, you could see how the final drive ratio has an impact on the launch performance. Higher the drive ratios, you will get a faster acceleration, but this will affect the top speed of the vehicle. And lower drive ratio has a reduced acceleration, but helps to achieve the top speed. So having the compromise between the acceleration and the top speed can be achieved with the help of the final drive ratio. So the next advantage is on the losses. As you could see the screen, the internal combustion engine with all losses combined together, we could see the power to wheels, it is only 16 to 25% of efficiency. But if you take the battery electric vehicle, the engine losses, auxiliary losses, and the parasitic losses are greatly reduced, which helps to achieve 60 to 65%. And also there is a technology called the regenerative braking, where the energy flows or the motor access the generator when the braking is applied, which in turn helps to recharge the battery. And by recovering those regenerative charges, EVs operate with an efficiency of 77 to 82%. So this has a greater advantage when compared to that of an IC engine. So let us now go into the technical stuff of electric vehicle. I'll take you through the high-level schematics and also the block diagrams of the EV. So the EV, to start with, it has the charging systems. It has the DC charging as well as AC charging. The DC charging, the power flow happens to the power distribution unit in the vehicle, and from there it helps to charge the battery. And there are different components in the battery, which we can see later point of slides. And the DC charging also helps in actually finalizing the rate of charging and other vehicle parameters with the help of communication to the vehicle control unit with the help of the PLCs. And the next type of charging is an AC charging. Usually the DC charging is used for the fast charging and the AC is a slow charging. So considering the battery systems is DC storage and having an AC charging, you need to have a rectifier which converts AC to DC. And that work is carried out with the help of an onboard charger. This rectifier has the fully controlled converters using insulated gate bipolar transistors. And this also communicates to the vehicle control unit and also helps to communicates to the power distribution unit and helps for the battery system charging. So the next is the MCU, motor control unit. This is nothing but an inverter. This uses the pulse width modulation technique, where we have the reference wave and the carrier triangular wave generated by the ramp generator. And we know that whenever the carrier wave is less than the reference wave, the pulse is going to be in off. And when the carrier wave is more than the reference wave is more than the carrier wave, we get the on pulse. So by just plotting that, we get switching on and switching off gate pulses, which helps to drive the insulated gate bipolar transistor. And we uses a 6-pulse inverter in order to achieve the DC to AC conversion in this case, which helps to drive the electric motor drivetrain. And all the other auxiliary units like the horns, indicators, headlamps, and other things are operated with the help of low voltage DC, which helps, which actually achieve with the help of a buck converter. So the DC-DC converter helps to convert a high voltage DC to a low voltage DC in order to support the auxiliary systems. And we also have the electric compressor in place of a conventional compressor in IC engine. And this compressor is mainly used for HVAC as well as the cooling system of the power electronic units and the batteries, and also helps for the cabin cooling. Since the battery performance greatly depends on the temperatures, even the cold temperature are not good for the battery usage, and we have the PTC heater, which helps to maintain the battery at an optimum temperature of use. And all these modules, we have the modules from the battery management systems, and the DC-DC converter, motor control unit, and the vehicle control unit communicates to the EV CAN, which in turn communicates to vehicle CAN with the help of the CAN gateway. So this is a block diagram. As you could see, the auxiliary power which gets from the DC-DC converter helps to drive all the auxiliary units like the indicators and the horns, and the motor is driven to the driveways with the help of the inverter. So that is the motor control unit. So now we will go for the system selections. The first system selection is the electric motor and the drivetrain. So electric motor converts the electrical energy that it gets from the battery to mechanical energy, which enables the vehicle to move. It also helps acts the working principle of a generator during the regenerative action, which in turn charges the battery. The electric motor and the drivetrain are chosen depending on the requirements, which includes high power, high torque, wide speed range, high efficiency, robustness, reliability, reasonable cost, low noise, small size, and we have many other factors that are considered here. Although the DC motor drives meet some of the requirements for EV application, due to lack in efficiency, bulky structure, lack in reliability because of the commutator brushes present in them, and also associated maintenance requirements made them less desirable. So with advancement in the power electronics and the control systems, different motor types emerged to meet the need of automotive sectors, out of which the induction and the permanent magnet motors are more favored for EV application. As we saw before, the transmission system, the final drive ratio of a single-speed transmission is optimized to meet the requirements of launch performance, maximum speed, efficiency, and drivability. So this is one of the examples of the electric motor that is used in Chevy Bolt EV. So this is a permanent magnet synchronous motor with a peak power of 60 kilowatt, and it helps to achieve an acceleration of 0 to 60 miles per hour in 6.9 seconds. So in this picture, you could see what are the different types of electric motors that is used in electric vehicle applications, and out of which the permanent magnet synchronous motor, due to the key advantages on the efficiency, the compact in size, high torque at the low speeds, and these motors are highly desirable for EV applications. So the next system is on EV charging. So as we saw before, both AC and DC systems are used for the charging. AC charging systems provides an AC supply that is converted to DC from with the help of a rectifier, what we saw before. This helps for the battery charging, and this is mainly used in home charging, and the charging with the help of this process is slow. Usually it takes 6 to 7 hours depending on the battery capacity and the rate of charging. So the next type is the DC charging. This requires a dedicated wirings and installations, as you could see from this figure, and this can be mounted at the charging stations or the garages at home. They have more power when compared to that of an AC system and can charge the EVs faster, and it usually takes 1 hour from 0 to 80% of the charging, and the battery capacity, it mainly depends on the battery capacity and the rate of charging that we deploy. In case of DC charging systems, we could see the permanently connected electric vehicle service equipments that we call the EVC cable. So that is permanently connected, that is mainly for the safety purposes. So these are some of the charging types and the reference standards, out of which the trend is nowadays using the combined charging systems, CCS of the type 2. So the next is on the energy systems. The batteries have been the major source of energy for EVs for a long time, and high energy density and the power density are the key consideration for an EV application. The fast charging, long service and the cycle life, low cost and the maintenance are desired in order to have the perfect energy source. And the parameters considered for the battery selections are the energy density. The battery energy density is the proportion of the energy that can be included in a volume. The specific energy is the energy per unit mass. The power density, specific power, cycle life, operating temperatures, how fast it recharges, and the fast charging time. These are the primary parameters considered for a battery selections. However, self-discharge, efficiency of the charging, and the maintenance are considered to be secondary goals. So now we can go through the battery pack architecture. The first component of the battery pack architecture is the cell. This is the basic structure of a battery system, which is the primary source of the power for the electric vehicle, obtained with the help of an electrochemical reaction. The electrical energy is obtained from the chemical energy through the flow of electrons, thereby causing oxidation and the reduction process at the electrodes. Next is the modules. The modules consist of cells arranged in a series and parallel combination, which is in turn determined based on the current and voltage requirements. Each module contains connectors with the supervisory unit circuits for the group of cells inside the module within the mechanical structure, as you could see from the figure. And the modules may also contain the junction box electronics with fuses, bus bars, connections, and relays. So next is the battery system. This is a complete energy source for the electric vehicles housed inside the mechanical restraints that consists of one or more cells, more modules, and the battery pack electrically configured in a series and parallel combination in order to meet the system requirements. It also has the cooling systems deployed inside the battery system in order to ensure and control the optimum working temperature of the cells. Also has the battery management systems, and high voltage and low voltage electrical configuration inside the batteries are accommodated inside the battery system with the help of the junction box. And we also have the protection circuits, thereby ensuring the safe and standard operating conditions. So as I explained before, the battery pack consists of the housing. This housing is made of an aluminum and steel, and the cooling systems in order to cool the batteries, and all the fuses, battery management systems in order to ensure the right optimum operating conditions for the batteries, and the modules what we saw before. So this is on the cooling systems. The battery thermal management plays a very key role in ensuring the battery performance in the EV applications. We have the ambient air cooling technology, forced air cooling, and the liquid cooling. Ambient air cooling is nothing but the passive air is just routed through the battery systems, and this helps to cool the battery. This is not considered to be a more efficient method, and because of which we go for the forced air cooling. So this allows the cooled air to circulate inside the battery pack, and is a good compromise between the cost and the performance. So considering the higher voltage operating conditions of the battery systems, now most of the EV manufacturers go for liquid cooling, which allows the glycol cooled by the refrigerant to flow inside the cooling plates inside the battery pack, and this is considered to be more efficient than both forced as well as the passive air cooling. However, the compromise is between the cost and cooling efficiency, and the cooling methods are chosen accordingly. So the next is on the battery management systems. The battery management system acts as the control system for the batteries, which helps to monitor for safe operating conditions. So as you could see from the architecture, it can be a single circuit which monitors and controls the whole battery system, or the master-slave arrangement to control and evaluate the parameters related to the state of health, state of charge, cell balancing, and safety monitoring of voltage, current, temperature, high voltage isolation, and does many other functions. The BMS communicates to other control modules of electric vehicles, so thereby ensuring the improved range, increased battery life, and also helps to have the controlling over the charging and discharging patterns. So we have the different types of the battery cells used in the electric vehicles. The first type is a cylindrical cell. The standard size is 18650. It has a steel casing. The cost of manufacturing is low, and it has a high energy density, high specific energy, and good mechanical stability. And we also use the pouch cell, and we don't have any standard size for the pouch cells. It depends on the manufacturers to decide on the size. The greatest advantage of the pouch cell is high energy density and specific energy, but the disadvantage is it is very susceptible to the moisture and high pressure. The prismatic cells is used with aluminum and steel casing, which has a decent energy density, and these are the commonly used in EVs. So now we can see the cell chemistry used in lithium-ion batteries. As we know, the lithium-ion battery is the primary electric source for the EV applications. However, the selection of cathode material determines the performance, efficiency, and the cost. So as you could see from the boxes, we have the anode. The primary composition of the anode is the graphite, that is a part of the carbon. And we also have the graphite with 1 to 3% of silicon, which helps to increase the energy density. And we also have lithium titanate oxide as an anode materials. And coming to the cathode, the cobalt content in the cathode is considered to add more cost to the cells. The first type is LFP, lithium iron phosphate. It has a long cycle life, high power, very safe, but the specific energy is very low in this type. Next is the lithium manganese oxide. It has no cobalt, so because of its low specific energy and cycle life, it is usually blended with nickel manganese cobalt oxide in order to get a better specific energy and the energy density. NMC batteries have high specific energy but high cobalt content, as we saw before. This adds to more cost, and these are most common cathode materials used in EVs. So the next type is NCA. The addition of aluminum increases the specific energy and the specific power. It has low cobalt content when compared to that of NMC. And these are the types of cells which are predominantly used in the Tesla cars. And as you could see the graph, how the energy density varies between the different cell chemistry. So now we can see the working principle of lithium-ion cell. As the name suggests, the lithium-ion are involved in the reaction driving the battery. We have the electrodes. Both electrodes in the lithium-ion cell are made of materials which can intercalate or absorb the lithium ions. So I call the word as the intercalation, because intercalation is when the charged ions of an element can be held inside the structure, as you could see from the figure, without significantly disturbing the structure as itself. The lithium-ion battery is generally constructed and starts its life in the state of full discharge. And at this stage, the lithium ions are intercalated within the cathode, and in this condition, the cell does not yet have the ability to produce any electricity. So before the battery is used, it has to be charged. As the battery is charged, the oxidation occurs at the cathode, meaning that it loses some negatively charged electrons. In order to maintain the charge balance in the cathode, an equal number of positively charged intercalated lithium ion from the cathode are dissolved into the electrolyte solution, and these in turn travel over to the anode, so where they get intercalated in the graphites. And this intercalation reaction also helps deposit the electrons into the graphite anode in order to balance the lithium ions that travels from the cathode to anode during the charging process. So during the discharge, the lithium ions are de-intercalated from the anode, and they travel back to the cathode with the help of the electrolyte. This also releases the electrons from the anode that were tying up with the lithium ions in the graphite structure, and these electrons flow through an external wire, providing the electric current that is used to carry out the useful work. And it's the connection of the external wire that enables the reaction to proceed. And at this state, when the electrons are free to move, so are the positively charged lithium ions also travel from anode to cathode in order to balance the movement of negatively charged ions and gets accumulated at the cathode. So when the cathode becomes full of lithium ions intercalated within them, the battery is said to be fully depleted and is flat. The lithium ion battery is recharged again, and this process gets repeated. The electrical energy or the charge, if we apply, then that pushes the electrons from the cathode to anode, which in turn moves the lithium ion from the cathode to anode. The cathode, we call it here to be the positive, and the anode is negative. This is an electrochemical cell, and the operation is opposite to that of the conventional voltaic cell. So this is one of the illustration what you could see here. The next image, like hope you're able to see this illustration. This has a lithium ion cell having the lithium cobalt oxide as a cathode, and the graphite is the anode. The lithium ion gets intercalated at the anode and the cathode back and forth during the charging and discharging, and the electrons flow outside the electric wire, thus providing the electric current and support the load. The cell reaction is shown below. You could see the positive electrode. Since the loss of electrons happens, the cathode undergoes a reduction reaction. So by having this reduction reaction, actually during the discharge, what happens is the intercalated lithium ion, it moves from anode to cathode, and lithium ions moves here, and the electrons, it goes through the outside circuit. So thus helps the cathode to get a stabilized lithium cobalt oxide. At the discharge, when you could see the anode, the electrons actually moves from anode to cathode, the loss of electrons. It is an oxidation that happens here. In the cathode, you could see the gain of electrons happens, that we call it as a reduction. This is a loss of electrons during the discharge oxidation. So the graphite structure, it gets back its graphite structures by de-intercalation of the lithium ions and electrons moving out of the graphite structures. So this is a reversible reaction. So thus we call it as a redox reaction. Like by combining these two actions, lithium in the graphite structure and the cobalt oxides, it goes to the graphite and lithium cobalt oxide. It goes back and forth due to the charging and discharging process. So now we can see the charging characteristics of lithium ion. So as we see in the previous figure, due to the small and light, a lot of lithium can be stored in both the electrodes, and this helps to achieve high energy density. And because of their high energy density and comparative lightness, stacking of lithium ions in one place contributes to achieve the battery pack, and it helps to achieve the high voltage which is required for EV applications. So the lithium ion with the traditional cathode material of cobalt, nickel, manganese, and aluminum, they have the charge of 4.2 volt per cells. Boosting the cell voltage increases the capacity, but going beyond the specified voltage limit, it stresses the battery and compromises the safety. The protection circuit built inside the pack, so they do not allow exceeding the set voltage. So in the first figure, we see the voltage and the current characteristics of lithium ions, how it undergoes during the charging process. So we have the rate of charging, which is governed by the C rates. The capacity of the battery is commonly rated at 1 C, meaning that a fully charged battery rated at 1 amperage hour should be able to provide 1 ampere of current in 1 hour. The cell manufacturers usually recommend the charging at 0.8 C, which will help to increase the battery life. So in this figure, stage 1 is the constant current charging, where the battery reaches the voltage peak quicker with the help of the constant charging. The stage 2 is the saturation charge, which takes a longer duration, and the full charge is reached when the current decreases to 3 to 5% of the amperage hours of the cell rating. With the higher current, the stage 1 duration can be greatly reduced, but the stage 2 will anyway have have a longer duration because of the reduction of the current moving from a higher value to 3 to 5% in order to get the batteries to reach the potential voltage. So in the standby mode, we can see when the voltage drops due to the parasitic loads in the systems, the minimum current gets applied to the cell in order to recover back the voltage drop what happens due to the parasitic loads connected to the system. So these are the 4 stages in the charging of the lithium ion. So in this figure, when the battery is first put into charge, the voltage shoots up quickly. The current is also constant, but what we could see here, the charge capacity is not actually increasing with that of the voltage and current increase. That we call it as a rubber band effect. This is mainly due to the impact, or this also due to the internal resistance that we have inside the battery. And when the internal resistance increases, and also when the batteries are charged at very cold temperature, this rubber band effect also increases due to that. So we may also have a question like overcharging the lithium ion, what happens? So by overcharging the lithium ion over the specified voltage limit, will deposit a metallic lithium on the anode, that we call it as a solid electrolyte interface, and the cathode material becomes an oxidizing agent, losing the stability and produces the carbon dioxide. The cell pressure rises, and if the charge is allowed to continue more, then the current interrupt device inside the battery system responsible for the cell safety disconnects the charging circuit. So the next is the discharging characteristics. The discharge rates of a battery is also governed by the C rates, as we saw before, and we have now energy cell from the Panasonic. The energy cell helps to achieve the maximum capacity in order to provide longer run times. As you could see, NCR 18650B, the energy cell from the Panasonic, has high energy capacity but is less enduring when it is discharged at the rate of discharge of the 2C. You could see the capacity of the battery is almost 3200 milliampere hour, but when the discharge rate is more, at the voltage cutoff, this we call it as the end of discharge. At the voltage cutoff range, when it is discharged at the 2C, the capacity drastically reduces, and it is able to produce only 2300 milliampere hour. And this also has the effect on the cold temperature losses. The ideal temperature, the operation of a lithium-ion battery is 25 degrees. When we say the 25 degrees, the percentage of charge existing in lithium-ion is 100%. It actually reduces to 83 at 0 degrees, and minus 10 degrees, 66, and it decreases so on. So the energy cell is primarily used for maximum capacity and in order to provide longer run times, and it is not capable of supporting higher loads or the instantaneous loads, which has more discharge rates. So the next type of battery is the power cell. So this has the moderate capacity, as you could see from the figure, because the rate of discharge here in the energy cell, it goes all the way to 3200, but it goes to 2000. But what you could see here is this support actually heavy load currents, even in the discharge of 1C, 2C, and the 10 ampere contributes to the 5C discharge. It has the capability of supporting at the standard specific capacity of the battery. So this has the moderate capacity but excellent load capabilities, as you could see. The power cells has lesser influence to the cold temperature as that of the energy cells. As you could see, even the minus 20 degrees Celsius has an impact of decrease only to 80%, but if you could see in the energy cell, it is 53%. So to meet the loading requirements, the pack designer can either use the power cells to meet the discharge C rates requirements, or go for an energy cell and oversize the pack. The energy cells holds about 50% more capacity when compared to that of the power cell, but the loading must be reduced in case of the energy cell. This can be done by oversizing the battery pack, and a method which is used in the electric vehicles. And in this case, the battery achieves exceptional runtime, but the drawback is it gets heavy and expensive due to more cells are used by oversizing the energy cells. So we have the future technology of the batteries, lithium-ion battery cell chemistry improvements. Even though the LFP lithium-ion phosphate has a lesser energy density, most of the OEMs go for this technology due to a lower cost, and also the cell-to-pack features without using the modules makes it more attractive. And also, we have some researchers like LG Chem working with the General Motors. So they are working on NCMA, addition of aluminum to NMC batteries in order to improve the energy density. And some other improvements in the lithium-ion chemistry is the anode, addition of silicon oxides with graphite, and the cathode NMC 811 and NCMA technologies. So we see there are still room for improvement in the lithium-ion chemistries. So we also have some technologies beyond the lithium-ion. So like the solid-state batteries, it replaces a high flammable liquid electrolyte. These are safer, high energy density, could be the next generation of EV battery. It also plays a major role working on these technologies. BMW's, SAFT, or the companies working on this solid-state batteries. Lithium air uses oxygen as the cathode. It has the highest specific energy. More issues with respect to this type of battery is the cycle life, low power, and Samsung and many researchers work on these technologies. Lithium sulfur uses sulfur as the cathode, higher specific energies. Main issues are cycle life, and sulfur has low conductivity and expands during discharge. And Sion Power, they work on this technology to see how they can commercialize this lithium sulfur. Also, other technologies are the titanium niobate and the sodium ion, magnesium ion combinations, and other improvements in the lithium ions are the use of the graphene. We call it as a supercapacitors. This also helps to achieve high capacity cathodes and the high voltage cathodes. So beyond the cell chemistry, we see the improvement in the battery pack by increasing the system voltage to 800 volt. This helps to reduce the I square or heating losses in the systems, due to which efficient, less heat generation and lower, thinner bus bars are used in this case. And the cooling improvements, immersion cooling, the battery cells immersed in the dielectric cooling. Liquid, we call it as the first phase cooling or outer circulation of the coolant. And we also have the second phase of cooling where the liquid boils. And we have now the technology of the phase change materials where the heat in the battery pack melts the phase change material to lower the temperature. And one of such examples are this type of wax that is extruded inside the aluminum structures. So with this, I will hand over to Ganesh to take you through on challenges and opportunities in the batteries. Thank you, team.
Thank you, Ram. Just if you can go to the full screen mode, please. So if you could see the overall challenges and the opportunities, some of the challenges that we have ahead of us is how do we make the electric vehicles more affordable and a lot more efficient? And how do we increase the electric vehicle driving range, which is a major concern, and electric vehicles initial cost of purchase, because electric vehicle seems to be people's mind, it's a costlier vehicle. And how do we have a good infrastructure for charging the electric vehicle, and especially for fleet segment, so the initial purchase, so they would need a lot more support from financing when they procure the vehicle. And we do have some challenges in localization of some of the key electric components, mainly from the power electronics side of it. So we do have some challenging barriers. And last one is recycling of the electric vehicle batteries after the end of life vehicle. So our job is to convert all these challenges into opportunities. For example, promote the Make in India concept and use the government's benefit like the FAME, which is the Phased Manufacturing Program, and the employment growth in power electronics and battery R&D areas. And the another reason why the previous chart you might have seen, the commercial segments are growing. So we need to move from the individual to the mass market transportation, because this will give you an operating cost efficiency like the buses and the fleet cars, for example, Ola or Uber. The new emerging business models are coming up. They call it as battery swapping, battery leasing, which I will take you through in the next couple of slides. And since the government is already giving a lot of benefits and the advantages, I think let's use the GST and the statewide government policy benefits in the EV manufacturing sales. So the last one is, so in order to address the recycling of batteries post their end of life vehicles, there are second life industries are coming up. For example, the solar power energy systems, the UPS, the battery storage, energy storage industries are trying to use the batteries, post the end of life, even with a slightly reduced state of charge. They can find a place to, use, can be used for the rest of the life. Next one, please. So it's on the challenges. So I will just try to cover on the key challenges and how each challenges will be addressed. So what are the challenges? The first and foremost challenges for the electric vehicle in India, at least, the range anxiety. The range anxiety is nothing but when a person drives an electric vehicle, so he should not have an anxiety in his mind. So will I reach my destination before the battery get drained off? That's nothing but the range anxiety. The second one is the cost of the battery. Today, the cost of the battery is approximately 40 to 50% of your vehicle cost. So the customer's concern is primarily, so how much of a warranty that I will get from the OEM if my battery goes off. So this is the important concern. So we cannot neglect that. Third one is charging infrastructure. When I take a vehicle on a highway, would I have adequate charging infrastructures, charging stations like the fuel stations? Would I have a charging infrastructure so that I can park my vehicle and get a charge? The second question is, how much of a time that I'm going to wait to get my vehicle charged to about 80 or 90% of a state of charge. So in today, the fact we know is India do have only about a 250 odd public charging stations in India. So these are all the challenges in front of us. Now, how do we convert all these challenges into opportunities? Let's see that. Next one. So the first and foremost on the range anxiety. So what you see it on the left-hand side is basically the electric vehicles and the range plot. So if you see most of the electric vehicles in the Western and the European countries, they are already offering close to about 600 kilometers per charge. This is the data based on 2019. That could be some more improvement. So for example, for one single charge, you will get about 600 kilometers. Let's compare the same set of parameters for the Indian vehicles. For example, Mahindra, Tata, Hyundai, but unfortunately, because of the battery size and other challenges, we don't see the range is not going beyond, on an average of 300. There are some vehicles where you see about a 452, but on an average, what you see is anywhere between 200 to 300 kilometers. So when you offer a lesser range, that's where the range anxiety comes in. So it is our duty to make sure the range anxiety is addressed so that the customer gets more range, so that he spends only a lesser money for operating the vehicle. So today, every Indian OEM, among whomever I just listed, everybody is working towards how do we maximize the EV range by various technologies, as Ram mentioned, through some battery pack size or a battery chemistry or reducing the weight. There are so many ways that you can increase the battery electric vehicle range, which we will cover at a separate topic. Next one. So the second advantage, I think Ram elaborately covered the battery market. So the battery demand is growing globally and annually. If you see the annual lithium-ion battery demand from 2015 to 2030, it's almost 3-4 times it's already increased. And of which, if we take the example of 2030, the passenger vehicles are going to demand a lot more batteries. The reason why? Because the passenger vehicle segment itself is growing, so there is a global demand for the battery. And another advantage, as Ram mentioned, so the battery pack price is coming down. So when we all started off this project way back in 2015, for example, the battery price was somewhere about the $400 per kilowatt. But today, you could see the price is almost halved. In 2020, we are getting somewhere about a $200 per kilowatt, but the prices are likely to go in the decreasing trend. So by 2030, so anywhere between $50 to $60 per kilowatt, it's going to be a reasonable battery price that we'll be paying. So there are two evidences why the EV segment is growing. One is there is a demand is increasing, the price is decreasing. So why not? We can take a lot more battery vehicles, and why not? We can address the range anxiety problem. So, and apart from the other factors, the battery chemistry is increasing, the higher density, energy density batteries are coming up, and there is a global trend in reducing the vehicle weight and as well as the battery weight with the improved chemistry. So these are all the opportunities that we have in the battery area. Next one. Next one. Ram? Hello? Ram? Hello? Okay, in terms of the opportunities that we have, so the public charging stations are increasing globally. So the side on the left topmost chart shows that, again, there is a tremendous growth in the public charging stations, especially the China market is putting a lot of money in setting up a public charging stations for electric vehicles. And their charging capacity and the charge rates are quite high compared to the India. So it is just for a comparison purpose, so we don't have to worry too much about it. But the point that we should note down is on the right-hand side, the Indian government is already aiming at setting up close to about 2,636 electric vehicle charging stations across 62 cities in India, so which is spreading across 24 states and union territories. This will happen before 2023. So not only that, the Ministry of Power has already given a proposal that there will be one charging stations in a grid of 3 by 3 kilometers in the city side, and there will be one charging stations, on every 25 kilometers on the highway, which is a slow charging. Similarly, there will be one more charging stations for fast charging method. Next one. So I'll cover the last topic, rather the battery swapping. So why the battery swapping is important. So one of the best way to address the battery range anxiety is go for a battery swapping. Swapping is nothing but when your battery is completely drained off. So go to a station, give the drained battery, get a new battery replaced in your car and keep driving. So that's nothing but the swapping process. So today the swappable batteries are possible, but the potential segment which is primarily using this battery swapping concept is two-wheeler and three-wheeler segment. India, there are close to 30 plus battery swapping stations operators are there for two-wheeler and three-wheeler segments. And what we see is the trend is going to the higher segments, like the buses are also now getting into the battery swapping mode. So the battery swapping is basically growing because it helps in the shared mobility space. So what you can do is in this whole model, like there are 3 or 4 people are closely working together, meaning the energy service provider, the vehicle manufacturers, the battery manufacturers, and we call the fleet operators. They're all working collaboratively so that it becomes a proper network. So not only private players, the public sectors like the NTPC, the Power Grid Corporations are also taking up this initiative, and they're also trying to set up the swapping and charging infrastructure so that the customer can get benefited about it. Yeah, next slide, please. So the battery leasing. So this is the last topic. So why do you consider buying a battery or leasing a battery of an electric car? So when you buy an electric car, as we mentioned, so the battery is roughly about a 50% of your total vehicle cost. So instead, there are companies in the Europe already started giving the option of, so when you buy a electric vehicle, you can buy only the vehicle. So the battery will not be part of your vehicle price. So it will be leased. For example, you can pay about a monthly $200 or a $300 as the battery price, for a lease price. So what is the benefit of it? So this helps you in completely disowning the battery from your electric vehicle. So first thing, your price of the purchase price of the electric vehicle comes down. The second one, the entire ownership of the battery, maintenance, warranty, it's been taken care by the battery manufacturer, and he will ensure the proper health conditions of the battery. So not only that, and your money that you will be spending, it's basically chosen according to your demand. For example, if you're using only a lesser money, you can choose a battery pack, which will be less costly for you. So these are all the advantages that you go for a battery leasing model. So this is very much useful if this same model can be adopted for India fleet segment, which is a lot more cost sensitive and price sensitive, where the operational efficiency is the key metrics for them to operate. So these are all at the early stages, but it is not too late for India to get into this model. So it is nearing. Next one. I think that's pretty much we covered. I think now we are open for any questions. Myself and Ram will be happy to take it.
Thank you, sir. The presentation was very informative. We came to know various aspects about BEV and ICE systems, and I thank you for sharing valuable information. Now it's time for queries. I request the participants to type your questions in chat box. We have questions coming in, sir. I'll read it up to you. Here is the first question, sir. Arun Prakash R. What are the main drawback of EV? Over to you, sir.
Say the drawback. So everything has got a two sides of a coin. It is like when you have some advantages, naturally there will be some disadvantages, but these disadvantages are at the earlier stage. For example, today I won't say disadvantages. So the initial purchase prices seems to be very higher. So the purchase price have to come down, but with the battery price coming down, as I said in the earlier charts, and also with the localization, so that part can be addressed. And the second one is the disposal of the electric vehicle batteries post their end of life. Again, there are some second life industries have already coming up in India. So that will find a way so that the efficient, the safe handling of the battery electric vehicles can be taken care of. And the third thing is primarily the charging and infrastructure. So the charging infrastructure, it is a kind of a chicken and egg, because the government is thinking we will see a lot more electric vehicles in the market. Then we will put something up in the highways or in the public places for charging stations. But the OEMs might be thinking, no, let the infrastructure first get stabilized, and then we will pump in more models. So I think both the government and the OEMs are now collaboratively working. So I would see this may not be a challenge anymore, because of the global regulations are coming up mainly for carbon dioxide reduction. So this will also be taken care as the hope. So that's pretty much the overall challenges, I would say. We are ready for next question, if any.
Okay, so we have the next question from Manoharan. The question is, if we could have a technology to supply energy for electrical machines indefinitely, why should we focus on a battery technology anyways?
Ram, would you like to take it from?
Yeah, hope you're able to hear me.
Yes, sir.
Can the question be more precise? What exactly is the technology are we referring to? Indefinite supply of energy to the vehicles. I'm not able to interpret the question.
Okay, so I'll repeat the question and we'll post on the comment section to ask the attender, the participant to be more precise on the question. I'll repeat the question once. If we could have a technology to supply energy for electrical machines indefinitely, why should we focus on a battery technology anyways?
I have not seen any technology which can supply energy to the machine indefinitely, because you need to have the source of energy, right?
Yes, sir.
So it has to be either a fuel cells or in case of an IC engine, it is the petrol or diesel, or in case of the batteries, in case of an EV, so then we go for the battery. So Ganesh, would you like to answer it, because I'm not able to interpret it?
No, the same comments. I think there is no technology for giving the energy indefinitely. So I think the question itself is not clear. Maybe if the participant is online, maybe he can speak up. While the time we'll the next question.
Sure, sir. Manoharan, please come out with the clarity in your question. So we'll move on to the next question, sir. The next question is from Harini. So please share your views on the transition from ICE vehicles to BEV in our country and the function of OEMs, government, and consumers in our country.
I think this was pretty much covered in the slide. I'm not sure. So the transition is already happening. You see every vehicle OEM who been traditionally manufacturing the ICE vehicles, whether it's a petrol or a gasoline, today almost everybody has got an electric vehicle portfolio in their product. So that itself shows that there is a trend happening on electric vehicle. So they would like to add an electric vehicle into the product portfolio. But you may ask, out of the 10 vehicles, they might have just one battery electric vehicle. So why is that? It is not the 50-50 percentage that whatever we are seeing it in the chart, but the market is demanding only that. So if there is a market demand is growing, that I want every vehicle or every next 50% of the population is demanding an electric vehicle, then you will see a lot more vehicles in their product portfolio. So it is basically a demand and the supply thing. So you can't completely remove the ICE vehicles, just overnight. It will take a lot more time than we expect. That's what even the government's vision of 30% or 100% of electrification by 2030 seems to be very challenging. So anywhere between 30 to 40% of electrification, to a battery segment, it'd be a lot more realistic. So that is one. And the function of OEM, government, and consumers, I think we covered. So OEMs are working, government is giving the subsidies, and the consumers, which is a major a key participant out of all the functions, the consumer's mindset is still not there. Reason being, I think, as we said, a lot of challenges, they have it in their mind. They have the range anxiety problem, they do have a charging infrastructure problems, they do have the cost of ownership problems. So all these things, I would call it as a myth. Probably they need a lot more clarity in understanding the electric vehicles. Maybe once that goes off, the consumer will understand this is the right technology to go about it, and they can, start choosing electric vehicles, to let them just to start with the electric two-wheelers or start using the electric three-wheelers. Yeah.
So as you said, most of the questions we have received has almost been covered in the presentation. So being from on the participant sides, we are just posting the questions again so that they'll get much clarity. So the next question is from Pradeep. What is the potential use of supercapacitors in electrical vehicles?
Okay. So we just saw some of the future technologies of the batteries. So the supercapacitors, or we also call it as an ultra capacitors. So these are the means to store and release the electricity. instead of the chemical form, they store it in the static state. And I'm not going into the working principle of the supercapacitors, but we also have an advantages using the supercapacitors. Supercapacitors already exist in the cars, which are driven with the help of the fuel cells with the regenerative braking systems. And this helps to rapidly store and discharge the electricity, handy for collecting energy that is getting generated by the braking and quickly releasing it upon acceleration. But they are yet to actually replace the lithium-ion batteries as the primary power source. But electric and the hybrid vehicles are advancing over the years. So we see an opportunity of supercapacitors to play a role, but it is not as of currently. Also, as we know, the supercapacitors pretty much rely on the physics rather than the chemistry to store their energy, and they don't actually degrade in the same fashion as that of the lithium-ion batteries. And one of the largest advantage of the supercapacitors over the lithium-ion or nickel-cadmium batteries, whatever may be, we are now speaking about charging the EVs in hours, but when the supercapacitors comes into pictures, then it helps for rapid charging. And also there is an advantages of with the help of the supercapacitors, it helps to achieve the wireless charging as well. But at this point of time, we see about the rapid charging and discharging, but the main issues in EV is with this supercapacitors, most alarming is the energy density. Sure, the supercapacitors can absorb and deliver lot amount of the power, but when compared to that of the lithium-ion batteries, but right now they are not able to store the energy as much as what the lithium ions does. So with this, I think we also have the technology of the graphene, which many OEMs are trying to extrapolate. And this technology, I think this will grow, and we'll have more usage of supercapacitors, which will help us to achieve a lesser charging time, and also the recover whatever the charge that is achieved with the help of regenerative braking, and that helps to have the faster acceleration of EVs, like how we have the turbochargers in the diesel vehicles. Hope that answers the question.
Okay, sir. So in connection with your reference, I would like to pose the next question. The question is from Arun Prakash. So in future, graphite battery replace lithium-ion battery. So will there be a replacement, complete replacement? So this is the question, sir.
I think the graphite, it should be the graphene batteries. That's what the supercapacitor batteries is referred to, I think. So that whatever I spoke, these are under the study of future technology of the batteries. And I think lithium air, lithium sulfur, and addition of magnesium, and usage of different cell chem, because as you could see the graphite structure currently, we saw about the solid electrolyte getting deposited at the anode by the usage of lithium ion over a period of time. This actually reduces the life of lithium ion. By usage of the supercapacitors, I think this problem will also be greatly reduced, and the life cycle of the battery can be greatly increased. And these are under studies, and we need to wait and see how the future technology arrives.
Okay, sir. Okay, so we also have a few questions from students. The question is from Jiva. The question is how to know the remaining life cycle of the battery or a cell. Knowing the remaining life of a cell.
Okay. See, usually the OEMs or the battery manufacturers in the electric vehicles, the package of the cells and usage of the cells, it is not up to the maximum capacity of the cells that is being used in the vehicle. We actually reduce the loading on the cells by increasing the number of cells in the vehicles. So if you take, if the battery has the potential of having from 0 to 100%, but actually the percentage what you could see from the instrument cluster is nothing but 40% to 80% of the battery, because the battery monitoring system is configured in such a way the maximum life of the battery, that is the lithium ion battery, is extended when it avoids the saturation of that rate of charging, what we saw in how the lithium ion gets charged. So we have the constant current charging, and most of the OEMs stops the usage of the battery at the constant current portion. So when the battery gets depleted, like over the period of time, what actually the battery monitoring system does is it expands the border of the lower and upper limit of the battery usage, which increases the life of the battery. But if you ask me whether the customer will know how many life cycles are remaining or how many life cycles are already completed, it is not as evident, because we have the control system, the battery monitoring system, which alters the bandwidth of the battery usage between lower and the upper grade or upper limits, which actually helps us to extend the life cycle of the battery. It is not one single number, and only because of that we could see the battery manufacturers or the OEMs are able to give a longer warranty period of 8 years. So this is not a one word answer to say 4,000 cycles were there, now it is reduced to 2,000, so remaining is 2,000. What actually does is we have a smaller band, and the monitoring system actually increases the band, increases the life cycle when the smaller band gets depleted over the period of time. So this is what happens in an electric vehicle.
Okay, so we have one last question. So the question is also from the student side. So it's not a question. They want to know about the flying cars.
Flying?
The answer is very easy. We don't know, or at least I don't know. It's not the expertise area of what we have. Flying cars.
Okay, sir. Okay, fine. So that's it with the question and a Q&A session, sir. So over to you, Anati, ma'am.
Thank you, sir. Thank you, sir, for sharing your knowledge with us. We would like to express our heartfelt thanks to our speakers. I request Mrs. Rajeshwari to give thanks note. Over to you, ma'am.
Thank you, Anati. Dear all, good morning to everyone. We had a very impressive, informative, and contentful presentation on the topic of electrical vehicle by Mr. Ganesh Shankaran, Chief Program Engineer, and Mr. Ramakrishnan Sivasubramaniam, Senior Engineer Program, both from Ford Motor Company Limited. It's indeed my great privilege to propose vote of thanks for this session on behalf of our institution. Our sincere thanks to the speakers who, in spite of their busy schedule, have agreed to provide a lecture in our webinar, that too in this difficult pandemic period. The participants, I would say, are extremely fortunate to listen and acquire knowledge about the trends in one of the upcoming technology related to the core electrical engineering, and that is electrical vehicle. We are very sure that this lecture is an eye-opener to the young budding engineers on this topic. The discussion highlighted the significance of electrical vehicle and the bright future scope for both the electrical engineering and electrical engineers in perfect. It's very impressive to note the government has initiated, or the government initiatives are in the direction of encouraging electrical vehicles. It's a nice move. All the technical concepts explained by you both enhanced our knowledge, sir, in this area. Thank you very much. All the questions posted by our students have been answered very well. We once again thank you so much for the pains taken in making our webinar an interesting one. hope really the participants would have benefited a lot. At the end, I would like to thank our correspondent ma'am, our principal ma'am, and our secretary for making this webinar to happen. Again, once again, I thank both the speakers who have given their valuable lecture and valuable inputs, which will be very, very useful to the young graduates. Thank you so much, sir. Over to you, Aditi.
Thank you, ma'am. Now we have come to the end of forenoon session. I thank all the participants for your kind cooperation and attention throughout the session. We have afternoon session at 1:30 p.m. I request all the participants to join back at 1:20 p.m. for afternoon session. Thank you all.
Thank you, ma'am. On behalf of myself and Ram, so we extend our thanks to you. So it was pleasure talking to you. Thank you so much. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you all. Thank you.
Bhaskar sir, can we leave?
Yes, ma'am.